Here's problem 1133. A coin with a diameter of 3 centimeters rolls up a 30-degree inclined plane. The coin starts out with an initial angular speed of 60 radians per second and rolls in a straight line without slipping. If the moment of inertia of the coin is 1/2 mr squared, in other words, the moment of inertia of a cylinder, how far will the coin roll up the inclined plane? Sounds good. Diameter is 3 centimeters, so the radius is 1.5 centimeters or 0.015 meters, and we have an angular velocity of 60 radians per second. Sounds good. We can treat this like a conservation of energy problem, and at the bottom of the inclined plane is point A, so we have the kinetic energy at A plus potential energy at A plus any work done along the way should equal the kinetic energy at B plus the potential energy at B. Now if it rolls up the plane, and let's look at this as an inclined plane like this, at some angle theta, and here's point A at the bottom, here's point B at the top, here's our height h, and it goes some distance d, which is the length of this hypotenuse of this right triangle. So as it goes from A to B, all of its kinetic energy will go into potential energy at B. So we'll have no kinetic energy at point B. There'll be no work done along the way by friction or anything else, and our potential energy by definition at point A will be our level height, so we'll have no potential energy at A. So our kinetic energy at A will be both rotational about the center of mass and translational of the center of mass. So we'll have 1/2 the moment of inertia about the center of mass times the angular velocity squared, that's our rotational kinetic energy at point A, plus 1/2 the mass times our velocity at point A squared, should equal our potential energy at point B, which would be mg height at B. Sounds good. So we have 1/2 times the moment of inertia about the center of mass, which is 1/2 mr squared, times the angular velocity squared, plus 1/2 m. Now the linear velocity at A is going to be the angular velocity times the radius. That squared is going to equal mg h. I have an m term in all of these, so if we divide both sides of the equals by m, we can get rid of the m's. And what we're left with is we got 1/4 omega squared r squared plus 1/2 omega squared r squared equals g times h. Or in other words, 3/4 omega squared r squared equals g times h. Solving for h, we have h is equal to 3 times omega squared r squared divided by 4 times g. So that is the height that we will go up this incline. And that height will be equal to 3 times omega, 60 squared, times the radius, which is 0.015 meters squared, over 4 times 9.8. And that's equal to 0.062 meters. That is the height that the coin will go up from point A to point B. Sounds good. But we want to know the distance that it goes up along the incline. Now if we look at this right triangle, we can see that this height should be equal to d sine theta according to trigonometry. D being the hypotenuse of the triangle. So d is actually going to equal the height h divided by the sine of theta. So this is equal to 0.062 divided by the sine of the angle, which in this case was 30 degrees. So this is equal to 0.124 meters. So that is the distance d that would go up this incline. 0.124 meters, or you could write that as 12.4 centimeters up the incline. So that's our answer. The coin will roll 12.4 centimeters up the incline.